So we have the same frame that we did earlier, but instead of looking at the horizontal deflection of E, we'll be looking at the vertical deflection of C, which we could kind of see would be something resembling that. It's a good idea to have an understanding of what the deflected shape is, even if you're not using the deflected shape. Just like the other video, let's change the units of our dimensions to match our units over here. So these will all change to inches. Just always good first thing to do so we avoid any problems. I think for this one, just like how we saw in the other one, we will do the graphical method. We could do we could do one or the other, but I feel like I showed in the last video that doing the graphical method is generally easier, especially with a simple beam like this. So first we want to draw our moment, well, yes, our moment diagram, but remember we're dividing it by EI, and that just kind of helps our calculations later. But alright, so let's look at our first member here, AB, this guy. We'll see that we have no internal moment, meaning that our moment right here, our moment diagram, will just be a straight line showing 0. Alright, and then that will be the same for over here. We could just go ahead and do the same thing. Say that is 0. Alright, so let's kind of just get an idea. If we were going to cut here between the discontinuities, creating a moment going up, so this will be coming down here with this being our point of interest. This will be our first M. What we'll have, oh, and we won't forget our 20 here and our 20 here. Where should we do this? So if we were going to sum the moments at that point, have M1, which would be this guy, positive. The 10 kips at that moment is pushing down, so it's also giving a positive moment, so it's 10. And that distance, that's our x2 guy, where this would have been x1, but we have no moment there, so just kind of skipped it. So this is our x value, it's just that distance. Then we'll look at this 20 kips, and that's giving a negative a negative moment. So that moment equation will be a positive 10x. And that'll be the same for the other side. Why did I put moment 1? Call that moment 2. And then moment 3 will also equal 10 to the x, and the bounds, not that it actually matters. But, so then when we're drawing the diagram, it'll look something like this. This top point being equal to, you'll just plug in 216 into x. You'll get 2160 over EI. Kind of be this top guy. Just like the other one, I like to do this first. We'll have these centroids be put like 2/3 the length of this. So I think it's 144. Let's go ahead and check that, because never hurts to make sure you're doing it right. Yep, 144 will be the location of our centroid, and that's on both sides because of the way we have it set up. Also be 144 inches going in, and then our areas, which will also be the same, we'll just call it A to make it easier. So it's a triangle, so we have 1/2 times the base, which is 216, times our height, which is 2160 over EI. Keeping EI is just in the variable form. Compute that area. 1/2 times 216 times 2160. Nice big beautiful number, which if you go back, because this is the exact same frame, and right now we're looking at the moments, so that's the area of each of these triangles, not just one of them, but if you cut it in half, and we'll have two of those, so we'll have A1, A2, actually let's make that match, so this will be A2, this will be A3, and we'll have 2. And then our next step will be to apply the virtual load, and we want our virtual load to go in the direction that we're interested in seeing displacement. Like I showed that vertical, or like I showed how the bending would look, that kind of going down. So we know that if this is C right here, our arrow, our point load, our unitless point load, it's going to look something like that. I think if we did something like this, we'd get a negative number. It should still work out right, but it's kind of want to have an idea of what our deflected shape would be doing, and then kind of match that with our point load. So now that we have this, it'll give us a better idea. And then, you know, if you wanted to, this would be 1/2 and this would be 1/2. If that makes it easier for you, just for bookkeeping, make sure you don't make any silly mistakes. All right, so now let's do the moment diagrams for our virtual load, which is what we just did there at C with that one point right here. This is our virtual load being applied at C in the vertical direction. All right, so looking at that, we'll look at what the moments are here. Again, in these vertical members, they will just be 0, just like above, because there's only the axial forces, which won't cause bending here. Keep in mind, axial forces would affect the deflection at C. Very, very little. It's just the compression throughout the entire member from that loading. It's just so little. And then our question over here, if we pay attention, says only consider bending deformation. So just going to look at it like this, so we get both of those, and then we'll look over at this other side and create a moment diagram for this guy up here. So let's think what that would look like, and if, you know, we wanted to be overly thorough, kind of draw the individual section cuts, or we can say, you know, where would we cut this to deal with it. And I think it's good to still use that kind of same X's going this direction. So this would be our first one, and this would be our second one, first one starting from the left and the second one starting from the right. So if we were going to cut this and have a moment right here, what would that moment be equal to? So let's just call that our first one. Kind of hate that doesn't match, actually. We'll keep that being our second one. So what that would look like if we were going to sum that up, we have only this guy right here causing any sort of moment at that section. And that would be causing a clockwise moment, which would be negative. And then when we bring that down to the other side, it'll just be this will just be equal to that, and the distance from the perpendicular distance, if we put out an arm to where this section cut is actually just that X value. We don't know, but it allows us to kind of do it. So this actually is the same on both sides though. So we'll just duplicate it. It's really similar to what is happening up top, just to like a smaller degree. Let me make sure that's correct. So then our moment equation here will be really similar, that kind of triangle. And we'll bring this down. This will be where our C is, and this will be the max. With this, you know, if we plugged in 216, we'd get being that value up top, the max. And this is actually in units of inches. You can do a check on your own. But what value we want to know is not this. We want to know the value at the centroid. So if we were going to follow this all the way down, saying we had them perfectly lined up, we want this value, which is when x is equal to the 144. So we'll plug that in over 2. What do we get? All right. And we'll have that the same on both. Both of these will be equal to 72. And then we use that equation, which is we sum up, oh no, I used the wrong size. Equation where we sum up this area times the value of m that is related to that same part or that same section. So we'll call this the area of that shape, the area of that section of our moment diagram, times the little m value when we put in the coordinate of x at the centroid for our original, or not original, but like real moment diagram. So we use this and to solve for our deflection at C. Again, purple, great color to do answers in. All right. Just get, oh, yeah, let's just get rid of all of this. I don't think we need it anymore. Let's give ourselves some room to do these calculations. All right, so the change in C, the vertical deflection, will equal to this times this, but we're doing it twice, and again, because the symmetry makes it easy, so 2 times 72 times that whole thing, all over 29 times 10 to the third, times the moment of inertia, and that's the same as doing it the long way, you know. This will be all the same, and then we would add another one, all the same. So let's put this into our calculators. 2 times 72 times all right, then we get 0.626 inches. And even though, so this is positive, just saying that the direction we chose our point load in, this direction, was correct. Even though, so we just confirmed that this was the arrow, it just kind of carries over. If we had done this way, it would have given us a negative number, which I think is usually, you know, if it's negative 0.626 and I told you that was the deflection at C was a negative number, you would guess it was pointing down. It's kind of the same thing that happens with most all forces. This sign convention just shows if we kind of assumed the right direction. All right.